submanifold.
Yeah, thanks, Tam, and thanks to the NCNGT organizers. It's been a really nice conference running now, I think, for the fourth iteration. So it's really exciting because I submitted a talk for the very first one, and now here we are in the fourth one. So today I'm going to tell you about hyperbolic manifolds and their embedded submanifolds, but I'm going to add here codimension 1. Okay.
Actually, so Michelle, before you really start, do you want to say anything about your preferences for getting questions?
Oh, yeah.
From participants?
So, yes, please feel free to ask questions at any time. I'll try to include some pauses, but also you can just start talking at any time. And if you write in the chat, I'll try to remember to look at the chat regularly. But if I miss it, if anyone else wants to let me know, that would be great too. Okay. So we're mostly going to talk about hyperbolic manifolds and their embedded codimension 1 submanifolds. Okay, so let me start by just giving you the setting. So here M is always going to be an n-dimensional manifold that's hyperbolic. So that means that I can realize it as a quotient of hyperbolic n space. And here is where gamma is a torsion-free and discrete subgroup of the isometry group of hyperbolic n space. So that's isom of Hn. And also of finite volume. Okay, so this is just the induced volume that you get from hyperbolic space when you take this quotient. Okay, so whenever we have this, then the boundary of M is either empty or a disjoint finite union of n-1 dimensional Euclidean manifolds. Okay, so what does that mean? Let me give you an example. So if you have, say, a hyperbolic surface, so this is a 2-dimensional finite volume hyperbolic manifold, then its boundary can either be empty or it can be a disjoint union of circles, since circles are the only 1-dimensional manifold. But then when you think about in dimension 3, when n is 3, then the boundary can either be empty or a disjoint union of tori, because tori are Euclidean 2 manifolds. Okay. So let me keep going. So in this talk, we'll be thinking about embedded essential codimension 1 submanifold. So let me tell you what this means. So W in M, so this is an n-1 dimensional, and this one's n-dimensional, is, or actually, let me say it a little bit differently. So I'm going to let this be an embedded essential codimension 1 submanifold. And this is what I mean by essential. What I want to say is that this embedding is pi1 injective. So in other words, it's incompressible. So in particular, I can think about this as saying that the fundamental group of W embeds in the fundamental group of N, but also incompressible. There's no compressing disks. I also want it to be not boundary parallel. So I said before that you couldn't have this boundary components that look like Euclidean manifolds. I don't want my essential submanifold to be one of those. Oh, I realized I'm missing a D, submanifold. And I also want it to be so that no component of W is a sphere. Okay. Okay, so let's start with some examples of what I mean by this. Let's say that n is equal to 2, Well, then here we're concerned about surfaces. So M is a hyperbolic surface. And what are the codimension 1 submanifolds in a surface? So they're one-dimensional. So we're just thinking about, and if I want them to be embedded, then I'm talking about simple closed curves. Okay, so W is a simple closed curve in M. Okay, let me draw some examples. So here is a picture of the once punctured torus. So I have a puncture here. If I were to consider, say, this simple closed curve, so this is a valid simple closed curve in my manifold, but as you can see, I could push it off to the boundary. So I do not consider this one. So this one is boundary parallel. So not essential. Okay, but I could look at, say, this curve over here. So this one is essential. Okay. So that's an example of something that can happen. Let me draw a different surface. Feel like most often when someone is thinking about drawing a surface, they draw a genus 2 surface. So here it is. So here's an example of a valid embedded essential codimension 1 submanifold. So that's an example that works. And here's a non-example. And this red one doesn't work because it's not embedded. Okay, so let me just remind you that a surface M is hyperbolic, or actually has a hyperbolic structure if its Euler characteristic is negative. Okay, and in this case, M has either no essential simple closed curves or infinitely many. Okay, so an example of a hyperbolic surface that has no simple closed curves is this one. So this is a 3 times punctured sphere. And there are no simple closed curves here that are essential. So the only ones that you could draw are the ones that are boundary parallel, but like I said, those are not essential. So there's really nothing that you can do here. So there are no such W, I'll say, in this picture. And any other surface that we have will have at least some genus in it, or will have at least 4 punctures in it. So you can actually draw some simple closed curves that are non-essential. So here's an example. Let's say the 4 times punctured sphere looks like this. We could have, here's an example. Or if we have something with genus, well, I guess I already drew some examples above, like over here or over here. Okay. Okay, so this is sort of what the situation looks like in dimension 2. Well, what about when n is equal to 3? So now M here is a hyperbolic 3 manifold. And W is an essential surface. Okay, so if you're a low dimensional topologist or 3 manifold topologist, or just a geometric topologist in general, you will have known that there's been quite a lot of history to studying essential surfaces in 3 manifolds, and they have helped us understand a lot of what's going on. In particular, in particular, three manifolds that contain essential surfaces are called Haken manifolds. And that's because in the 1960s, Haken proved that these manifolds with these essential surfaces, they can be successively cut along these surfaces so that eventually, after finite amount of steps, all the pieces are three balls. So this is what is called a Haken hierarchy. And this idea of starting with these manifolds with these surfaces have led to many important results in three-manifold topology. So having these essential surfaces gives you a lot of information. And now, after the more recent results of Agel and Wise, we know that actually all hyperbolic three-manifolds, even if they don't contain an essential surface, there's some finite cover of them that will, okay? Okay, maybe that's all I'll say about this. I can't really draw hyperbolic three-manifolds. But if you'd like to see sort of ideas of what they look like, there are videos out there where you can fly inside of them. So you could see that. Okay, and what about n at least 4? Okay, here is where things get a lot more complicated and we don't really know as much of what's going on. And part of one of the big reasons why we don't really know what's going on here in terms of hyperbolic manifolds and their embedded codimension 1 submanifolds is that we don't actually know very much about hyperbolic manifolds of high dimension. So I'll say, as a caveat, we don't know much about high dimensional hyperbolic manifolds. Okay. Since we don't know very much about them, well, what do we know? We have a few methods that we know of how to construct them, but we don't even know how to construct all of them. But let me just tell you about a few ways to construct them. So 2 methods for constructing hyperbolic manifolds. Okay, so the first one, method 1, is through tiling by Coxeter polytopes. Okay, so let me start with a definition. So a Coxeter polytope P in Hn is a finite volume convex closed subset of Hn, which is bounded by hyperplanes. So these hyperplanes look like copies of hyperbolic space 1 dimension down. And these correspond to sort of the faces of the polytope. And furthermore, we want that any 2 faces that meet will meet at angle, or let me say dihedral, will meet at dihedral angle pi over n. Oh, not m. Let me use a different letter, m. Okay, so here m is a positive integer. Okay, so then the set of reflections on the faces of P generate a discrete subgroup of the isometry group of Hn. Okay. So in particular, this also means that P tiles Hn. Okay. And so one way that we can construct manifolds is that if we have a Coxeter polytope, we can use tiles of this corresponding to a manifold cover. So we'll get a manifold that's tiled by these tiles P. So let me draw an example. So here's an example in H2. Okay, I'm doing this example in H2 because I can draw in H2 and it gets a little harder to do that in higher dimensions. But also because I have an iPad, it helps me draw a perfect circle. So that's nice. Here we go. Okay, so here's an example in H2, and this is using this model of the H2. So here, this is a hyperplane. Here's another one. Oh, sorry, this is moving. Here's another one. They meet here at a right angle. Here's another example of a hyperplane. Let's say I have something like this. Let's say something like this. Or something like this. So here's an example. So if I look at this polytope in here, well, I have right angles at these three edges, or sorry, at these three corners. And over here, note that they don't really meet in H2. So these points are in the boundary of H2. They're not in H2, so they don't meet. So here's an example of P, a Coxeter polytope.
Do you always want finitely many edges or faces of your poly?
Yes, I do. Okay. Okay, so now notice that we can form so like I said, we have the reflections on the faces, they generate a subgroup. So I can reflect on these faces because these all correspond to these hyperplanes in H2. That means that I can reflect on them, and this is an isometry of hyperbolic space. So I'll say here that the reflections on the faces, they generate a group, let's call it gamma, in isom of Hn. Okay, and this grid is going to be discrete. So let me say this here, it's discrete whenever this is a Coxeter polytope. But actually, if I look at the quotient of Hn by this gamma, this is going to be an orbifold. So it's never going to give me a manifold as is, but I can always find, let me say, we can find manifold covers as long as we take a cover of a degree that's high enough to get rid of all those orbifold points. So this is one way of finding manifolds starting from a Coxeter polytope. And here is something that I should notice. So note that hyperplanes corresponding to the faces that these will correspond, oh, I said the word corresponding twice, but these will correspond to immersed submanifolds, or let's say codimension 1. Submanifolds, okay? So as you can see in this example, this hyperplane is going to correspond to an embedded, to a curve in my surface but the curve might not be embedded, but it's going to be immersed, okay? And in fact, they're not just codimension one submanifolds, but they're also totally geodesic. So let me give you actually a definition of what I mean by this. So if I have, again, this is dimension n minus 1 and dimension n. And this actually, let me say it here. And here, W is a hyperbolic n minus 1 dimensional manifold. Actually, sorry, I'm gonna keep that. Is called totally geodesic if the following is true. If every geodesic in W is also a geodesic in M. Okay. So that's what we mean by total geodesic, and this has a couple of implications. So the first one is that whenever this is true, then this is going to be pi1 injective. Okay, and that's not hard to see because, like I said, the elements in the fundamental group, they correspond to these geodesics in W. So if they're also geodesics in M, then you get this injection of the fundamental groups. It's going to be pi1 injective, and in particular, it's going to be essential if you assume that it's embedded. And furthermore, it also corresponds to saying that, let's say the image of pi1 of W is going to fix, so it fixes a hyperplane H n minus 1 in H and the universal cover of M. Okay. Okay, so again, like I said, one of the methods of constructing higher dimensional manifolds or just hyperbolic manifolds in general is to start with a Coxeter polytope and look at the group generated by its reflections and take some sort of manifold cover of that. So we're going to get a hyperbolic manifold that is tiled by these Coxeter polytopes. Okay, so great. We can try to find these and we can use these to construct hyperbolic manifolds. But unfortunately, I'll say it like this, unfortunately, hyperbolic Coxeter polytopes don't exist for large n. Okay, so in fact, this was shown by Winberg. So this is in the early 1960s. So it's quite a long time ago that compact Coxeter polytopes don't exist. For n, I think at least something around 30. And then not long after that, this was extended to finite volume ones. Prokhorov, and independently Khovansky. And this is in the late 1960s. So the same is true for just finite volume. Coxeter polos, they don't exist for n at least something around 1,000. So the number is like 990 something, but something around this. So they don't exist in high dimensions. So the method of constructing hyperbolic manifolds using these Coxeter polytopes, it just fails in any dimension. We can only do it in some lower dimensions. Okay, so there must be some other ways to construct hyperbolic manifolds in higher dimensions. And let me just go on to the next page. And here I'm going to talk about another method. And this can be method 2.
Michelle, can I ask a question real quick? Sorry, can you scroll up
Yeah.
a little bit?
Mhm.
I have 2 questions. One is, can you say again what the connection was between totally geodesic and the Coxeter polytope? And then the second question is, how hard is it to know if you have a totally geodesic embedding in general? Like, is it hard to know you have one? Seems hard, but I don't really know.
Yeah, so let me address your first question first. So when I was describing that one way of constructing hyperbolic manifolds is to start with a Coxeter polytope, well, it turns out that these faces corresponding to a Coxeter polytope, because these are hyperplanes in HN, when you look at either your orbifold or your manifold that's built out of copies on this Coxeter polytope, those faces are going to correspond to immersed submanifolds in your whole space, and they're going to be totally geodesic. And that is just from the fact that they're coming from these geodesic hyperplanes.
Great. Okay, thanks. Sorry.
Does that answer your first question?
It sure does. Yeah, thank you.
Okay, great. So they might be immersed, was one point that I said. But you can always try to find some sort of cover where they live to something embedded, but they're there. And then your second question was about how hard is it in general to find total geodesic submanifolds? It's hard. Or is it hard? The question was, is it hard? And the answer is yes.
I think the question was like, that's one version of it. I think the other version was like, if you had an embedding, can you how easy or hard is it to tell that it is totally geodesic?
I see. I would say that it's probably easier to find totally geodesic submanifolds than it is to find submanifolds in general.
Oh, okay.
In some ways, and in particular in the way in this example, when you construct them out of Coxeter polytopes, you find them this way. But in the second method that I'm going to describe, they're also easier to find.
Great, thank you.
Yeah. Okay, so here is method 2 for constructing hyperbolic manifolds. And this method, I'm just going to call it arithmetic. Okay. So to tell you how to construct this manifold, I also have to be a little bit aware of time, because again, I can't look at my iPad because it just says 9:41, and that doesn't change. Okay, so there are a few different ways that we can use arithmetic or to sort of construct hyperbolic manifolds, but there is one particular way that makes it really nice to actually study embedded submanifolds in there. And to do that, I first have to describe for you real quick what is a model, or how to think about hyperbolic space in higher dimensions, because I think it's fairly common for people to have seen how to construct, say, hyperbolic plane or the hyperbolic 3 space. But in general, here's a method that works really well. And it's called the hyperboloid model. Hyperboloid model for HN. Okay. So here's how we do this. So we start in our n+1. So this is Euclidean space of dimension n+1. And we look at the following form on vectors in r+1. So let me just say it like this. X is in a vector in n+1, where this form looks like this. Okay, so if we think of our vector x having entries x naught, x1, all the way to xn, so we can look at this form on the vector, and I can look at the space of all vectors where this form has value equal to -1. Okay. So what is the space? If you've taken Calc 3 recently or taught Calc 3 recently or TA'd, you should know that this is a two-sheeted hyperboloid. So here's a picture of what it looks like when n is equal to 2, just because that's the easiest one that I can draw, or the only one I can draw, really. I guess I could draw one dimension lower. Okay, but we have this two-sheeted hyperboloid, and this is what it looks like when you set this form equal to 1. But I'm going to identify, it has two sheets. So let me say here, this is the positive sheet and the negative sheet. So I'm going to identify Hn with this positive sheet, okay? And I'm going to give it a metric that looks like this. So the distance between two vectors that are in this sheet, this is going to be arc cosh of the following bilinear form. Minus fx minus f1. Okay. And it turns out that when I look at this upper sheet with this particular metric, this gives me a model for hyperbolic space. Okay. So you could, if you want to, also compute that we do get this constant curvature of -1, which is what we expect from hyperbolic space. Okay. And if we do it this way, then it's easy to see, well, what is the isometry group of Hn. So these are going to be matrices that preserve this metric and that preserve this form. So these look like this. Oh, actually, I'm going to write it like this. So what I mean by this is that this is the orthogonal group that preserves this form. And this plus here is meant to indicate that it's preserving the upper sheet. So you're not like sending the upper sheet to the bottom sheet. But like I said, we can write these as matrices. So these are just matrices A in GL n plus 1 R, where if I look at this this form, I can also has this associated diagonal matrix that looks like this. Again, so there's a -1 for this -1 here, and then +1s for all of these. So that if I look at A times that matrix times A transpose, this gives me back that original matrix. Okay. So this is what I mean by matrices that sort of preserve this form. So we, oh, and I also want to say, that's all I wanted. Yeah. Okay. So this is what this looks like. And it's sort of not hard to see then what do the hyperplanes look like in this space. So hyperplanes, so Hn-1 hyperplanes. So they look like orthogonal complements to vectors V, where when I evaluate this form at this vector, I get something positive. Okay. Okay. And I'd like to note that I picked this particular form that has signature -1n. Okay, so in particular, when I look at its corresponding matrix, I have exactly 1 negative eigenvalue and n positive eigenvalues. And I could have picked a slightly different form as long as it has the same signature. So this works just as well with any other quadratic form of signature n-1. Oh, sorry, n1. Again, this is meant to say n positive eigenvalues and 1 negative. Okay. Okay, so in this sense, what I get is I still get hyperbolic space. Okay, so now I'm going to tell you how we can now use this to construct lots of different manifolds. And here is the here's the point that if so let's say that if F is a quadratic form, and let's say that it's defined over a field K, which is totally real. So this is a subfield of R, which is totally real. And what this means is that if I take if I look at any other embedding of this field, the image always lands in R. Okay, so I can do this, and if, okay, so then if I now look at my group, but I look at now just the entries that land in the ring of integers. So here I'll say this is the ring of integers in K, but I could, for example, set K equal to the rationals, and then the ring of integers is just the usual rational integers. So this is the one that you should keep in mind if you haven't thought about this before. Then this is actually going to embed discretely in the following. Okay, so I'm going to get a copy of all of these groups. And what I mean when I do this, I just mean thinking about it with that particular embedding. Okay, so like I showed you before, whenever this form has signature n1, this whole space is going to be a isometry group of Hn. However, when this form has signature, when it's positive definite or negative definite, when it's a definite form, then this whole group is actually going to be compact. So in particular, so if sigma is definite for all sigma except 1, and for that particular one, F has signature -1, sorry, has signature n1, then this group is actually going to be discrete in isometry group of Hn. So what does that mean? That means, let me just call it gamma F, because it corresponds to F. So i.e., if I look at the quotient of Hn by gamma F, this is a finite volume hyperbolic orbifold. Okay. So now I have given you again a way to construct a hyperbolic orbifold, and you can take finite degree copies of it to get now something that's a manifold. Okay. But this one comes with this particularly nice way to define it using this arithmetic, which comes from this quadratic form that I defined for you. But something that's really interesting about this one is that we can actually see, I'll say here, we can see immersed totally geodesic submanifolds from the hyperplanes that look like this, where, again, remember that I wanted this to have positive value. And then this is going to sort of close up to a finite volume n-dimensional one, codimensional one submanifold whenever V has entries in this field. Okay. So this gives us a way to sort of seeing all of them all at once. Okay. And then we can apply, I'll say this, here's a theorem of Darren Long in the 1980s. And it says that immersed totally geodesic submanifolds lift to embedded submanifolds in finite sheeted covers. Okay, so what this is saying is that once you find an immersed total geodesic submanifold, you know that there's some finite sheeted cover of your full manifold where the submanifold is going to lift to something embedded. So this gives you a way of constructing hyperbolic manifolds with embedded submanifolds. Okay. But notice that you have to go to a finite sheeted cover to get this. So then we can ask the following question is, when are these submanifolds embedded? Okay, and in particular, because it says that we have to go to a finite sheeted cover, whenever we do this, we're increasing the volume. So here's a sub-question to this. Should we expect that this only happens for large volume? Okay. Okay. So now let's go back to talking about some of the examples that we saw before. So before, when I talked about the case when n is equal to 2, so we're asking now about surfaces with simple closed curves that are in them. So let me say this again. We have surfaces here. So what is, I said the Euler characteristic is always negative. So what is the smallest possible volume? So small volume. So smallest volume surfaces are the following two. Are of area 2 pi. And there's exactly 2 of them. So I'll give you the picture again. So I drew this one earlier. So this is the 3 times punctured torus. And the once punctured, the once punctured torus and the 3 times punctured sphere. So in this case, we have no essential simple closed curves. And in this case, we have infinitely many. Okay, so we saw that earlier. And this is the entire picture of what happens for the smallest area surface. Okay. So if we think now in dimension 3, if we now think about what is the smallest volume, 3 manifold, then this is what is called the Weeks manifold. So this is a manifold that has been studied for a long time. It has volume somewhere around 0.97. Okay. Oh, sorry, 94. And this manifold is small, and small is another way to say that it has no essential surfaces. Okay, so there's just no essential surfaces at all. And in particular, it's not going to have any essential surfaces that are totally geodesic. Okay, but what about the smallest volume? Non-compact hyperbolic 3 manifolds. Okay, so there's actually 2 of these. One I can draw for you. So here's a picture of the figure 8 knot. And if we look at its complement in S3, so this is a hyperbolic manifold. So this is the figure 8 knot complement. And we can also look at its its sibling manifold. So this I can't draw for you. It's not a knot complement, but it's another 1 cos hyperbolic 3 manifold. So these are the 2 3 manifolds, hyperbolic 3 manifolds that are known to have smallest volume. So this is volume is around 2. And it's also known that both of these are small. Are small, again, in the sense that they have no essential surfaces. Okay, but they're also arithmetic in the sense that I described before, that you can construct them from these quadratic forms. So I'll say here that, however, they have infinitely many immersed, totally geodesic surfaces. Okay, just none of them are embedded, but they have infinitely many that are immersed. And because of what I said before, you can always find finite covers where some of these immersions will lift to embeddings. But again, when you're going to a finite cover, you are increasing the volume. So because of this, I'm going to pose the following conjecture. And here's a conjecture that I'll give you. So let's say, again, that I have M, a hyperbolic manifold. Oh, actually, let me say, I want this to be a minimal volume hyperbolic manifold. Also, and let me add orientable. And arithmetic. So then, if M contains a closed, embedded, totally geodesic submanifold, then N must have been 2, and M is the 3 times punctured torus. Sorry, 3 times punctured sphere. Okay, So what am I saying here? I'm saying that that the only time that I'm expecting a minimal volume hyperbolic manifold to contain a totally geodesic embedded submanifold is this case that I described up here. Okay. Okay, so let me actually pause for questions right now.
Did you want the one torus instead of the 3 times punctured sphere?
Oh yeah, that's right, sorry. The once punctured torus. Yeah, you're right. I'm sorry about that. So this one has none, and this is the one that does have some.
Oh,
Yeah.
Michelle, do you also want closed in so both of no closed essential surfaces for the figure 8 knot and the sibling?
Yeah, sorry. Do I want closed for
So,
W? Yeah.
for the figure 8 knot and its sibling, like in the description under.
Oh, in here I should add closed.
Thank you.
Yes. That's right. Yes. So this is a question about whether minimal volume hyperbolic manifolds can contain closed embedded codimension 1 submanifolds. Oh, I meant to say codimension 1. Okay. So let me mention a few things about, well, why do we expect this to be true? Well, I just show you what is the picture in the case when n is equal to 2, and I've shown you what is the picture in the case of n is equal to 3. Why am I including this word arithmetic here, which I didn't exactly define? I just give you an example of how you construct these. And well, actually, all of those cases that we saw above in dimension 3, they happen to be arithmetic. So there's always an expectation that minimal volume manifolds are arithmetic. And this is because arithmeticity sort of gives you a lot of symmetries, which means you can cut down by symmetries to get to a smaller volume. Okay. Yeah. And why am I restricting myself to total geodesic submanifolds? Well, like I said, in general, it's hard to construct submanifolds, but there's at least some things that we can do when we try to find total geodesic ones. Okay, so I do know that I'm almost running out of time, but I'll give you this fact first. So I'll state it as a fact / a proposition because it does require proof. But if n is at least 5, and then m is hyperbolic n manifold, again, satisfying all these conditions here, so minimal volume, orientable, and arithmetic. So if m, so let's say this, if m is cusp, then m does not contain any closed, immersed, totally geodesic submanifolds. Okay. So what am I saying? This don't exist in dimension 5 and above. I already showed you what happens in dimension 3. So that means that this conjecture reduces to the case of n is equal to 4. Okay. Yeah. Okay. So now in the last 2 minutes, maybe I'll state one quick result. So now we know that if we want to ask this question, we have to understand what happens in the dimension 4 case. And something that is true in dimension 4 is that there is, we know what the minimal volume of a hyperbolic 4 manifold is, and this corresponds to having Euler characteristic exactly equal to 1, but we don't know how many manifolds achieve this volume. So here, minimal volume and 4 have all the characteristic equal to 1, but we don't know how many such M there are. But we do know some of them. But we do know a family, an explicit family, I'll say. An explicit family of examples of hyperbolic four manifolds that achieve this minimal volume. And here I'm going to end with this. So this is a theorem joint with Alan Reed, is that none of these contain closed embedded totally geodesic codimension 1 submanifolds. Okay, and note that by none, I mean none of these examples. So not in general. Okay, so it just gives some evidence for this conjecture. And I'm out of time, so I'm going to stop here.
Thank Michelle. Please, if you have questions, use the raise hand feature. And then we will call on you to ask your question.